Okay, so today what we're going to do, we're going to finish what we started on the semi-classical expansion of the path integral, and then we go to perturbation theory, okay? So let me maybe remind you. So what we did last time, so the central object of the path integral approach right now is what we call the propagator. And what we have done is so this, I wrote it K, and it's from starting on x prime, tau prime, to a final space-time point, x prime prime, t prime prime. And of course, this is just the matrix element of the evolution operator, time evolution operator. And so what we did on Friday was to write this as what we call a path integral formulation, okay? A configuration path integral. And so the result is that what we get here, it's this formal expression. What you remember that to get it, we split the time interval into n time interval of equal duration. And then we end up with this kind of expression if we take formally a limit n goes to infinity. Okay, we're here. So what we say is that the path integral is under all paths satisfying the boundary condition. So meaning that x of tau prime has to be x prime. Okay, so this is a kind of formal expression. So usually to do explicitly a calculation, you go back to the definition in terms of the limit, okay? And so we computed explicitly this path integral in the case of a free particle. And we have shown that indeed the free particle, the propagator can be written as a term in terms of exponential of the action evaluated at the classical solution times something else. Okay, so this is usually, and this is a kind of general feature that this path integral is going to be this kind of factor, where here it's the classical solution time another factor. Okay, so then since we have this, let's look at the semi-classical expansion, okay? Oh yeah, that's true that it's not working. And you're just looking at me, you could. What? Oh yeah, I know. Okay, sorry. So it's not working. So, yeah, so let's just summarize quickly what we did last time, and then applied this to the specific example. So we were looking at paths which are like can be written under this form. Well, this is the classical solution. And this is just the fluctuation. So there was one question in the homework was, why here are we considering this square root of h bar here? So there are maybe different level of answer, but one answer already is that usually what we want to do is try to approximate everything with going back to Gaussian, okay? And here you can see that if you use this square root of h bar here, the dominant term is going to be the term, a Gaussian term, okay? And then the first correction is going to be the term in with the potential. So let me write maybe the result, and you're going to see. So here, if now we look at this, we get this expansion for. And then the interpretation of this square root of h bar is then going to be also that, in fact, this is related to Brownion's movement, so I'm not going to give much more detail here, but this is... So here we get, again, this term, okay, where it's a classical action evaluated at the classical part, and then we're going to integrate over all perturbation, all fluctuation, where now the fluctuation satisfied at the boundary, it's vanishing at the boundary. And we have this kind of term where here we're going to see that, in fact, this is like just a kind of Gaussian integral. There is no one here. Okay, and then the first correction is going to be when this is evaluated at x is equal to x. So we see that in the correction, the only thing appearing here is going to be the potential. And for example, we're going to apply that now to the harmonic oscillator, where the potential is just quadratic. So this term is going to disappear. And in fact, indeed, we're going to see that applying this expression in the case of quadratic action. So quadratic action can be computed exactly as a path integral, okay? And in fact, we're going to see that even if here we have a kind of perturbative approach, the result we're going to get is exact, okay, in the case of the harmonic oscillator. Okay, and maybe let's just recall what is this A here, this operator. So is the M and the second derivative of with the delta. Okay, so this is what we have seen on Friday. And now we're going to see what we can do with that explicitly. So first, maybe a few remarks on this operator and the way we're going to deal with this, this term, okay? And so here what we need is the notion of okay, because here, so what are going to be the main things to do to evaluate this? So we will have to determine what is the solution, okay, the classical solution, then evaluate the action as the classical solution. So this is just a classical problem. And then we have to deal with this term. And to deal with this term, the way we're going to do is to try to find eigenvalue for this operator, okay? Because so this was one of the questions of the homework. Then if we get the eigenvalue here, you really see that then this means that this, this operator can be seen as a diagonal operator, okay? So here we're not dealing with finite dimensional matrices, but we're dealing with a kind of infinite dimensional operator. But if we have a kind of, we find the eigenvalue of this operator, then this just means that this object is like a Gaussian integral, where, of course, the result is going to be written in terms of the determinant, which here is going to be a product of eigenvalue. Of course, then there are always issues of regularization, because usually we're going to have an infinite number of eigenvalues, so infinite product is going to be infinite. But yeah, there are different approaches to deal with, to regularize this object, but we're going to see one in a specific example. But so first, let's just recall the idea. What we want to use here is that, so first, let me remind you that if A is n times n Hermitian matrix with positive eigenvalue, then usually what you can, and we wrote eigenvalue. Really what we want to generalize is this kind of expression, where you know that here, this is a generalized Gaussian with okay, but here the dimension is go from 1 to n, okay, and then here you get that this is just where the determinant can be written as a product of. So this is what we want to generalize. So now we are dealing with, let's call an operator. And so we're going to define, so this is kind of a definition. We define the determinant of the operator O by, so here we will have to think about kind of regularization. Infinite product of its eigenvalue. So usually, sometimes we denote the determinant with capital D instead of a small d to say that we're working with an operator. So we're going to say that this is okay. So now let's consider an explicit example, and maybe things are going to become a bit more less abstract than what we're doing now.
Where does the regularization come in? Is that in?
So here there is no regularization yet, okay? And we're going to see that in the example we're going to deal with. In fact, we're just going to consider again. So what we want to consider is to compute the propagator for the harmonic oscillator. But again, we are going to use the fact that we know the propagator for the free particle, okay? And so divide by that, and then it's going to be a way to get rid of the infinity in this product. But otherwise, there are different methods to regularize it here. So here, indeed, it's just like the formal definition, okay? And I haven't mentioned the regularization procedure yet. Okay, so let's now look at the harmonic oscillator again, okay, where I haven't written what is going to be just and the potential now is quadratic. And as we said, so we want to use this expression here, and we're going to see that it's going to allow us to compute, in fact, in this case, the exact propagator for the harmonic oscillator. So what are the two steps that we need to do? We need to first compute. And here we're just really dealing with only a classical problem, okay? So we have to find the classical equation of motion, solve the classical equation of motion, and then compute the action, okay? And then the second step will be to find the eigenvalue of A, meaning that we want to find a kind of eigenvalue equation to solve the eigenvalue equation of this form. Is going to be lambda okay, so let's start with maybe the first step. And here, so it's quite simple. So the equation of motion is just sorry, it's omega squared. And we have boundary condition. So here we consider that xc of rho prime is x prime. And so I give you, so this is quite straightforward. It's just a very simple so I'm going to denote by big T is, okay, just to simplify notation. And so here we get, if I have already implemented, of course, the boundary condition, omega okay, so it's first forward to check that when T is equal to so T is equal to tau prime, so this term vanish, and then here you get the same as this one, so you just get x prime, and the same for tau prime prime. Okay, so no. Then, so the object we need to know is the evaluation of the action with this classical solution. Okay, so here usually the way, in order to avoid to compute a kind of we can in fact simplify that just doing, since we are interested in the evaluation at the classical action, we can do first an integration by part, like this. One of the term, we have less term to compute. So let's just do this trick. So here we want to compute this object, and so sorry. Omega squared. Okay, so now what I'm doing is an integration by part on the first term. So what I get is just that we will have to evaluate at plus something that in fact is going to vanish, because we're going to make that this is going to be xc time okay, and here you can see that this is the equation of motion. So since we are interested in the classical solution, by definition this is equal to 0. Okay, so we just end up with this term, and so it's very simple to just use this solution evaluated at the different point, and what we get is, of course you need to compute the first derivative, but this simplifies a lot the calculation. Okay, so this was the first step, and it's really just Again, I'm using big T as a total time interval. So this is the result we're going to use. And of course, you can check that when omega is equal to 0, you just recover the free particle case. Okay, so I'll let you check this. So any question now? I guess this is quite easy right now. So now let's look at the second point. So we want to find the eigenvalue of A. So this means that we want to, so if now A is equal, so in the case of the harmonic oscillator case, this just eigenvalue equation is just going to simplify into so again, it's a simple differential equation we need to solve with the boundary condition. Don't forget about boundary condition. And here, so I give you, so we're going to get the following function. And you can check that indeed that the boundary condition is simplified, and if you plug this solution into this equation, you get the value for lambda, which is just where here n is any integer different from 0. Again, T here is the total time interval. Okay, so we have all the ingredients now. And to compute this object, okay? So here, in the case of the harmonic oscillator, this term, there is no such term, and we just need to evaluate this. So we have this evaluation, and now, again, this is going to, now, since this is diagonalized, more or less, if we can see that as an infinite dimensional operator, then it's just a Gaussian, so it's just going to give the inverse of the determinant, okay, which is, so, again, in order to avoid now divergences, as I said, usually the way you do when you compute a propagator is to, you compute a propagator with respect to a propagator of a system that you already know, okay? So in the case of the, here we're going to use the free particle one. So in order to avoid differences here, we normalize and it's going to be a way to regularize the determinant here. So this means that here we're going to look at this object divided by the propagator for the free particle. So I use this notation. The 0 means V equals 0. And so if we go back to this expression, what we're going to get? We're going to get that okay, so this is the evaluation of the classical action at the classical solution. Then since you remember that this term was equal to, as I wrote it here, so for the free particle, we've shown explicitly that the propagator can be written as an exponential of the action for the free particle evaluated at the classical solution. Okay, so here I'm going to, since I'm divided by that, I'm getting a plus where here it's the classical action with V equals 0 and the classical solution with V equals 0. Okay, and then the rest of the term we can show that we're going to get a product, so it's a determinant of the operator A for the harmonic oscillator. So we're going to get the product of this lambda n with a square root. And here, since we're dividing by this one, in fact, the same calculation could be done when omega is equal to 0. Okay? And yeah, a second. And here, what we would get is this. We would obtain the same result with now lambda n 0 is going to be just this term. What do I get? Sorry. Pi. Yeah, Amelia.
Sorry, could you write a bit bigger as I'm struggling to read them?
Yeah, sorry. So where?
What does it say at the top?
Here?
Above that.
Okay, so let me maybe move that first.
Okay.
So you're here? Yeah. So now in order to avoid divergences, I just say that we normalize by the case V is equal to 0. So that's why we look at this object here. Okay? And now, of course, we're going to use the fact that we know this value. It's just that now what I use here is that this propagator can take exactly the same form as here, okay, without this term, with A now given by the same thing with just putting omega equal to 0. So if you do the same calculation with omega equal to 0, you end up with the same eigenfunction, and the eigenvalues for V equal to 0 are going to be exactly the same, except that you don't have this omega squared term, okay? So here, if now we look at the ratio between the two, this can be written like this, with now we have to compute this factor, okay? And of course, so any question? Yeah.
So I see the analogy between the multivariable Gaussian and this, but it's not obvious to me that you can do the same thing if you're integrating over functions rather than variables. Is that?
Yeah, so you're right that here we're working with functional and not just like matrix with number, but so your question is if I can justify a bit more why.
Should we just believe it?
But
is there ever a case where you can't just do that, or?
No, so here if you yeah, I don't know any case where you cannot do it, and I don't really see any. Okay, I could give you a justification why it's working or not. So really, yeah, because really all this idea of really even the perturbation theory or anything with path integral, the only thing that we know how to compute are going to be Gaussian. So really the idea is always to try to go back to Gaussian and then have kind of correction. So it can be semi-classical correction that as here, or we're going to see in the perturbation theory that it's different correction. And so, yeah, this object is always kind of used, and I've never seen any, I don't have in mind any example where it won't be working. And okay, I keep that in mind, and in case I find something, reading something, or just thinking about it to explain that better, I will come back on that. Okay, so everyone, except the issues that indeed here we're dealing with this functional determinant and everything. Everything is clear and up to here for the calculation. Okay, so now let's compute this explicitly. And of course, it's where it would have been great to have another blackboard. Okay, so I'm almost done for this part, and then I will give you 2 minutes break before starting the. So here it just. So this means now that my propagator, or what I call K of is going to be equal to the one for the free particle times and the product now can be just written as a product over n of okay, and then of course this we know the result is something written as a factor. As we already mentioned it, it's going to be a factor time so these two terms simplified, and now I can use the fact that this is a well-known result or at least it has been computed many times, and here you get that it's a finish. So combining here everything, okay, using the result that was here in this box, this expression, we get finally this expression for the harmonic oscillator, and we're going to use it in a moment. And an exponential of, so here now I'm just using the expression of S is omega t, h bar, and then okay, so this is the expression of the propagator for the harmonic oscillator computed using the path integral formalism, where here, in fact, it's the exact result. Okay, and so this is important. Any quadratic action can be evaluated exactly using the path integral thing, and it ends up that even if here we started with a perturbation, a classical perturbation expansion, first this term vanish, and even if this could be seen as a perturbative term, it ends up that it's in fact the exact term. And there are other kind of way to compute this. So usually also what you can see to convince a bit yourself is that instead of just looking at here a perturbation, you could anyway say that all paths could be written as the classical solution plus another path, let's call it y of tau, which will anyway satisfy the same boundary condition. And then you can do really a change of variable here, and you will see that you really have a splitting where you get this object times the same object, but now evaluated at y, and then you can either go back to the definition of the path integral, but at the end you end up with the same result. So this is just a way to compute this path integral. Okay, so I'm going to do a very short break because we have a lot to cover. Well, do you need a break? Or? Yes or no? So if it's yes, you do that, and okay, there is no yes, huh? So sorry yeah, don't be so shy, huh? If you wanted to have a break, and now it's too late. And okay, and I'm writing too small. Is that what you're telling me, Amelia? I was changing seats. Yeah, but I guess it was quite clear. Okay, I'm going to try. But the point is that I don't have so many blackboards, so I can try, but I can try. Okay, so now I really want to go to the perturbation theory because, in fact, most of the path integral, you won't be able to compute them exactly, so you will anyway go to a perturbative approach. And even if in quantum mechanics, perturbative theory via path integral is maybe not the simplest, so simple, and there are other approaches that maybe are easiest. It's really mimicking what you're going to see in quantum field theory. And also, of course, if you're just interested in the first correction, sometimes you can get the first correction by other means. But if you really want to have additional correction, then it's become more and more efficient. Okay? So I'm going to keep that because we are going to be interested. So this is for propagator for the harmonic oscillator. And in fact, what we're going to look at now, it's an explicit example to see how the perturbation theory can work and give you a few methods that anyway you're going to use a lot in the quantum field theory course. And the example I'm going to take is going to be the anharmonic oscillator, meaning that I'm going to add a correction to. Okay, so and we'll see that, in fact, even in quantum theory, we can talk about Feynman diagram at some point. Okay, so now it's the second part. So part 2 for today, which is perturbation. In the path integral formalism. And the explicit example we're going to take is look at this action. So the anharmonic oscillator, which can be written okay, so you cannot compute the path integral, the propagator for this action exactly. Okay, so you need to go to the perturbative to do. You can do just a perturbative expansion of that in lambda. And in fact, so in the tutorial this afternoon, you're going to look just if you consider instead of the path integral, just if you consider the ordinary integral with so the Gaussian term, and you add this quadric term here, you will see that even this, you cannot compute it exactly, even as an ordinary integral. So you're going to use the same method that we're going to develop for the path integral for this ordinary integral to expand it in terms of lambda, okay? So this is going to be the first question of our tutorial this afternoon. And then, so what is going to be the question we're going to try to answer? So of course, I'm going to give you, we're going to compute the propagator for this action, okay? But as an expansion of another action. So the idea really of this method is that since we cannot compute that exactly, we are going to write this in terms of we are going to write the propagator associated with this action in terms of a propagator we know to compute. And this one is going to be a harmonic oscillator with a source term, okay? And we're going to see that indeed, if we just add a source term, we're going to be able to compute. And this one can be seen as using derivative on the other propagator, we're going to be able to compute this propagator. But so here, what we're going to try to figure out is, so in the homework, you're going to do that for any energy level. But here, we're just going to focus on the ground state for this anharmonic oscillator. And the question is, so can we get this at least at with a correction in order 1 in lambda, okay? So we're going to try to compute this now. So how can we extract that, okay? So let's, for simplicity, we are not going to compute, we're going to, of course, to extract that from a propagator, but we don't need to compute any propagator. We can just look at a simple one where we're going to look at this case. So we're going to extract so in most of the literature, usually you're going to see that you use the partition function, but we're going to work with the partition function tomorrow, so I'm not going to introduce it. But here I'm going to use this very kind of trivial propagator, which is a propagator from the point 0, 0 to the final point 0, and then I'm going to use here big T, which I'm going to introduce this beta. So it's going to be the propagator from. Okay, so just here, the choice of spatial point being 0 and 0 is arbitrary. What is important is they are the same. Okay, it's going to simplify a bit. So what do I mean by this? This means I'm just looking at this object. And here I'm going to introduce, to show you how you can extract E0 of lambda, I'm going to just add the resolution of the identity using the eigenvector for the energy, okay? And so indeed, this can be written as a sum over n, okay? Where here I'm going to get minus beta En. So if here it's the one with lambda, times a product of just eigenfunction and so from here you can extract E0, because so you see that since we are working with so what is important here is that we are really working with the Euclidean time. So meaning that here we don't have any I anymore, okay? Everything is real. So you see that here, this sum is really going to be dominated by the term with the ground state energy, okay? So here this means that E0 can be seen will be obtained when you take the limit beta goes to infinity of 1 over beta. And then we're going to take the log of and to get this, in fact, we're going to now compute this as an expansion. So an expansion in terms of lambda, okay? Okay, so let's, any questions here? So what is now the trick we're going to use? The idea is really to express this propagator in terms of a propagator that we know how to compute, okay? Okay, so what is the idea here? And you're going to see that you're going to use that a lot in quantum field theory. The idea is to express this is a very
You're using beta as 1 over tau or as tau?
yeah, tau times the h bar here, okay? No. The time is h bar beta, okay? So that's why here you don't have any divided by.
Still with the big rotation.
Yeah, still with the big rotation. So I have done the weak rotation from the first lecture, and I'm going only to work with Euclidean time. But anyway, we're going to see tomorrow that one important object is going to be the partition function, where in fact the partition function is just the trace of the propagator, but when the weak rotation has been done, okay? So in fact, this limit is exactly the same if instead of k here, now you replace that with z of, and z of, usually we parameterize this with beta, where beta is going to be with unit time divided by h bar, okay? Yeah, okay, so this seems quite as a good idea, but how can we do that in practice, okay? So let's first define the path integral for the propagator we will know how to compute, and then I'm going to show you why it's interesting to work with this path integral. So here is the path integral for with the source term, and so this means that we're going to, and I'm going to call J the source, and this is exponential so it's a harmonic oscillator, and I add this term linear in x now. So still can be seen as a Gaussian integral because this term is going to be, we're going to be able to reintroduce it. So indeed, we're going to be able to compute this path integral the same way we computed the harmonic oscillator. And in fact, if you think about what is going to change in the computation we just did, since if you remember what was the expression of the operator A here, you see that the operator A is with the derivative second of the potential, and here, so this term won't be visible, okay? So this means that in the calculation we did before, the second part of the calculation really remains the same, okay? 0.2. The only difference is going to now compute the classical solution and the evaluation of this action on the classical solution. So and this is what, so to compute the classical solution is what you're going to do in the tutorial this afternoon. I'm going just to give here the step. But so first, why is this interesting? Okay. Why? Okay, we know how to compute that, but how can we relate that to this object? Do you know? Have you already seen that? Or? How can I write? So as I said, the idea is to express this one in terms of one we know how to compute. I'm telling you that we're going to use this one. And I'm telling you that indeed you can compute it exactly the same way we computed the harmonic oscillator one. So do you know how you get here?
Functional differentiation.
Sorry?
Functional differentiation with respect to J.
Yeah, and then putting J to 0. Okay, so indeed here, I'm telling you that this is equal. So from now, I'm just going to, because I'm going to lose track of the H bar anyway, so let's put it equal to 1 for simplicity. And then at the end, we'll reintroduce it when we will deal with the energy in order to have something with the right unit. But otherwise, for sure, I'm going to lose some H bar somewhere. So let's simplify things. And so we're going to work. So exactly, we're going to use differential functional derivative of with respect to J.
Sorry.
Yeah.
Are we using lambda over 4 factorial or just lambda? Because over there you define just lambda. Over there.
Over there, which is somewhere. Yeah, so let's. Thanks. Good point, yeah. It's a typo in my lecture. Yeah, so let's use with the 4 factorial. Thanks for consistency. And indeed, so it seems that some of you are already familiar with that. Just to convince you, if you just look at this, let's just look at the functional derivative of this propagator with respect to J. What do we get? We're going to get that indeed and then the same thing, okay? So the same action. I'm going to rewrite it. It's just S over here. So this object is, yeah, it's, so this one is the one with the lambda. So yeah, sorry. Here, this one is okay. So you see that indeed that the action, if you act on this propagator with the derivative, it has for effect to put a factor x outside. So of course you can repeat that, and even for any arbitrary functional f, okay, usually if you consider f this action on the functional, then of course what you're going to see where you keep the same action. Okay, so really here, the idea. So the f we're going to choose is this exponential of minus then the integral over d tau of lambda and this this functional derivative here. So this is what we're going to do. And then, of course, usually we're just going to be interested in the perturbative expansion. So in practice, we're just going to look at the first order in lambda. So what we're going to get is that then we're going to put j equal to this is the first order. And then, again, put j is equal to 0. But so you need, and this is going to be the first order in lambda. Okay, because so what we want to compute here is going to be just the first correction for the ground state energy. So we just need the first order in the propagator here, okay? But you see that what we need now is this object. We need the explicit expression of this propagator. So as I said, you're going to do some of the steps in the tutorial. So I'm not going to give you every step, but I'm going to give you a bit what is the idea. Yeah?
So this method only works if you have a perturbation which is a function of x, right? Like not a function of derivatives of x.
Yeah, the way, so the term, where are we? So if here instead of, well, first it has to be polynomial in only, I think, I would say one variable. But then, because you see that the derivative we're going to use here is going to be with respect to this field, the j here, this functional. So what you put here in front of is what is going to go out, okay? So you still have some flexibility here, okay? Because depending on the term you want to get here, it's more or less what you're going to put after your action. But of course, the idea, also one important point is that you want to start with something you know how to compute. And you're right that if it's then a first derivative or even something more than quadratic, then we won't be able to compute it exactly, so this method doesn't have any use, okay? Really the idea here is to be able to write the one we don't know how to compute in terms of something we know how to compute, okay? So the restriction more come from this being what can we compute exactly, and in fact, except Gaussian path integral, we don't know to compute many other things in using the path integral, yeah.
Question. So shouldn't there be a delta t minus t1, tau minus tau1 in the functional derivatives as well?
Here?
Yeah, on the right-hand side. So when you take the functional derivatives.
Yeah, no, we're going to see explicitly that you don't have to. It's just any tau1, and it's going to simplify. We're going so any tau here. Okay, so here I'm integrating over.
I know, I'm just, yeah, that one. When you take the functional derivative, shouldn't there be also a delta tau minus tau1, which will cancel out the inter...
Yeah, you're right. Okay, so or otherwise it's already...
Yeah, there is a delta.
It's already tau1. It's already tau1.
Yeah, so to cancel out the integral and the tau. So that you get the same thing.
Yeah, so here, I guess... yeah, so you're saying... Well, it's this, yeah. Well, sorry, yeah, we're going to do an explicit example. So here I'm getting confused if I have too many integral or if it's... if I already simplified. Sorry, but so is that correct now? Or?
I would say so.
Yeah, I think it's. And then if we. No, but in fact, I don't have any more. So it means that I already done it. In fact. Okay. Sorry, because I don't have any integration anymore in here. So here. Okay, so this is, in fact, if I don't have tau 1 here, this is correct. And sorry, yeah.
So then in your final expression there, in the first order term, do you still have the integral for d
The first order term?
in lambda? You're integrating over d tie there.
Yeah.
Right.
Thank you. This is. Okay, thanks. So So the important point here is that we have to find an explicit expression for this k of j and as a functional of j. And so you will do in the tutorial most of the steps, but here let me. So we need, this is what we need. As a functional of j. And so as I mentioned, we can really use what we have done for the harmonic oscillator. So in fact, you can. Maybe let's give you a few steps. So if I first, of course, I'm going to, at some point, need some normalization, and I'm going to use the normalization. So let's go back to normalization of the harmonic oscillator. So here's the zero mean j equals 0, but it's still the harmonic oscillator. Okay? It's not the free particle. So let me. So this term, as I said, is going to be exactly as this one, meaning that it's going to be the exponential of a term with the exponential of the action evaluated at the classical action. And the other term is going to come from this A operator. But the A operator is going to be exactly the same that in this case. So in fact, if you take the ratio, it's going to simplify, and you just end up with where here it's the action with the source term plus the action for when j is equal to 0, but it's still the harmonic oscillator, and the action for, so here it's still harmonic oscillator, okay? Where this term is exactly what we just computed here. Okay, so now I can really simplify, get that my k so here I'm giving you the expression for any more general, okay? So not only when x and x prime prime are equal to 0. So here, it's just to give you an idea why it is this expression. So we're going to keep this term, of course, which is the one that you're going to compute in the tutorial. And then we just end up with some normalization, which come from the case with the harmonic oscillator. So it's the same factor as Okay, and so this factor is exactly the one we computed for the harmonic oscillator. Okay, so what does it mean now? If we go back to the case where x prime prime and x prime are equal to 0, then this means that my k is of the form, I'm going to call this term like c. It's a constant, but it's going to be, at some point the value is going to be important, but it's just because it's a constant of j, okay? And here we're interested of this function really as a functional of j. So the j is going to appear in the evaluation of the action. And so if you look now at the equation of motion starting from this action, compared to the case of the harmonic oscillator, okay, so where is my action? My action is just here. So you're going to get that it's the equation, instead of just the homogeneous differential equation, you're going to get a different inhomogeneous differential equation, okay, with just the term j. And so here you're going to show that in the tutorial, because we also take the assumption, so here it's important that x prime and x prime prime are equal to 0, we're going to see that in fact this can be written in terms of, formally, it can be written in terms of a green function, okay? And really the green function comes from the fact that now you have this source term. So the differential equation you're looking at, okay, is so this is a formal expression of our propagator, where here, what is this function? So this j is the green function. Satisfying, of course, the equation of motion. Which is so the delta. And yeah, you also have boundary condition, okay? So the this explicit calculation is what you're going to do in the tutorial, and then this means that formally your equation, your solution, you know that now. So maybe is going to be, so the solution for the harmonic oscillator plus so the x is going to be, yeah, just of the form okay, so this is going to be the your formal solution. Then of course you have to deal with boundary condition and this kind of thing. Okay, so this is the object we want to use. And we will have to take functional derivative of this object. Okay, so let's now just check that the notation are going to be clear and see which term is going to contribute. So any question here? So here, to compute explicitly that and what is G, okay? So see tutorial. Okay, so let's maybe keep this one. Okay, so now the next step is to take functional derivative of this object. So before that, I want to just check with you. So to make sure first that so the next step is to take but before that, let's make sure that we understand how functional derivative works and if the notation we're going to use is clear. Okay, so let's maybe first look at, so this is kind of, and then I'm going to give just a result, even if it's quite similar. Just, for example, just look of so let's first act with, so we're going to take twice the functional derivative with respect to J of this object, okay? So let's do the first derivative. So this means that we're going to be left with one derivative. Okay, so what do we get here? How can I act with my G of tau here? Yeah, because I can either act on the first one or the second one. Okay, so what I get here is, if I keep for the moment, and this was the delta function that Patty was mentioning, here we're going to get that indeed it's so this is if I'm acting on the first one, but I could also act on the second one where I would get and so of course this now I can simplify my delta, so I get only one integration left. So the first one, let's go the plus something like the integration over. Now I'm using this delta on tau 2, so I get just tau 1 tau. Okay, so this is quite simple, and now I can do the same with the remaining derivative, and it's going to act the same way exactly on both terms. So at the end, what I guess is only, and it's going to make happening another delta function. So then this means that I'm just having kind of diagonal term for the green function. Okay? And so for us, now we want to compute the functional derivative on this kind of object. Okay? And you see that the functional derivative, we're going to take four derivatives, okay, of this object. So this means that we want, and then we're going to put everything to 0, j equal to 0, okay? So this means that we're interested only in the term which is quartic in j. So this means that here we are only interested in the term I think I swapped notation here. So this object here was the one I was calling before, no? Sorry to get you confused, guy, but I think is that the case, no? Because yeah, this is the object that we are going to perform the perturbative expansion and express this one. So here it's not this one yet. So of course it's the middle one. So sorry. And we want to take the functional derivative on, yeah, anyway, this is correct. It's just the name I use here. Okay, so now we want to use the term okay, so this was the warm-up. Now we want to take functional derivative of and we're going to take 4 of them. Okay, so this means that the only thing we are interested in here, and then take 4 of them, and then we'll put j is equal to 0. So we are really only interested in the term which are quartic in j, meaning that we want to find. So we're going to get something and that I can say that is going to be irrelevant for us, plus c times, and it's going to come from the quadratic term in the expansion in lambda. So no, in lambda in j, sorry. So prime, well, here I am going to get square. Okay. So this is the term that is relevant for us to take the differential derivative. The functional derivative, sorry. And so you see that it's very similar to what we have done here, except that now it's 4, and we're going to get a product like this. So if we do something very similar, at the end what we get so now I'm using the right notation. So this term in the first order, as we said, is going to be when j is equal to 0 minus lambda over 4 and again j is equal to 0 here, plus some additional term in lambda square. Okay, so almost there. So if now we compute the functional derivative, and the only term important to compute this functional derivative on k0j is this one, we just end up with this is going to give us C times 1 minus, and then the 1/8 come from here, so it's 1/2 times 1/2 squared, so it's 1/8. And then here I'm going to get, taking all the functional derivative, okay, so in the simple example I took, I obtained it's equal to twice the green function, kind of the diagonal term of the green function, and here I got that it's 4 factorial times the diagonal term of the green function squared. Okay. Okay, so and then we of course get some. So this seems now quite simple to compute. So you're going to see that this term, taking into account, since at the end what we are interested in is taking beta goes to infinity. This means that when you're going to find explicitly what is this green function, instead of taking, so let me maybe. Yeah, so here I told you that the green function is solution of this equation above with this given initial condition. And you will see that if you really want to find the solution with this given initial condition, it's not so, well, yeah, the expression is not so easy. But in fact, since what we are interested in here is just to look at when the time, so tau 1 is going to go to plus or minus infinity, okay? Because we want to look at beta goes to infinity. In fact, you will be able to look at the green function only with initial condition, meaning that this is vanishing at infinity. And then the expression is very simple. You're going to find, so this is tutorial. You're going to get that here. So I'll let you really check in the tutorial that you end up with this solution. And so now we can write really explicitly what is this propagator. And we end up with something like C times that can be, since we want to take, so now the next step, we want to compute this. So we want to take the log of k. So let's write this as an exponential. Since anyway it's at first order, still valid, we get that this is this exponential. So this is 32. Yeah, maybe it's small. So it's m squared omega squared. Okay, so what do we get? 32. Where here, since this is in a constant over tau, in fact, the beta comes from that when you perform this integration here, it's just going to, what you're going to get is the time interval duration. So here it's beta, okay? So here it's going from, we said 0 to beta, okay? H bar is equal to 1, so beta is like time here, okay? So this was this object that we are computing. So since this is independent of tau, we just get that this is, we keep that times the time duration, the time interval. So we get the beta coming from here, okay? And then the omega squared come from this. And in fact, yeah, the m 1 over m was coming from the expression over there. So I think I'm been missing it. Yeah, so the 1 over m squared comes from there. So in fact here when we perform this, sorry, there is a 1 over m here, okay? So it's here, so then it ends up being here. Okay, so then we can just conclude by taking the limit when beta goes to infinity. Then, of course, now C is not anymore a constant because it's a function of beta. But so anyway, this is going to give you that it's of log of C minus omega square. And this term, so maybe I should remind you what is the C here. C is a function of okay, so since you take the log of this fraction, this product, okay, the only and then you divide by beta, and beta goes to infinity. The only term which is going to contribute is the one with hyperbolic sign here of omega beta. And of course, the sign is just the sum of two exponential, one with a plus, one with a minus. So when beta goes to infinity, only the one with a plus is going to contribute. So you're going to get a exponential log of exponential omega beta. And then you divide by beta. So you're going to get the first term. This term, in fact, is going to give you the grounds, the ground state energy. And this term is the first correction. Okay, and so if I finish here, oops, sorry, you can really see, so the 1/2 comes from this power here. You're going really to get 1/2 of, and this term is going to give you the omega. You have the minus sign compensating that it's at the denominator. So you get the omega, and then you get the correction, the first correction, which is given by this one with the, with the minus. No, with the plus at the end. Yeah, minus, minus. And here you're going to get okay, so now if you want to have the correct dimension, you need to reintroduce the h bar. So here it's omega h bar. So this indeed is A0, 0, meaning that this is for the harmonic oscillator. Okay, so this is h of lambda, and this is at the first order. Of course, this term is not, the units are not correct. So if you look at the unit of lambda, m omega squared, then you need here h squared. Okay, so meaning that here you have the first correction. Okay, so this calculation, the way it's done is quite important, in particular to be able to write explicitly what is the solution of this equation of motion in terms of the green function. So this is what you're going to do in the tutorial. So I'm going to post the lecture note online. Like this, hopefully, it's going to help you to follow. But yeah, the tutorial is not just prove me that. It's you have a set of questions, and hopefully it's going to help you to go step by step.